Okay, so welcome all for this. So firstly, I should thank Rajesh and the Kotak Center for this afternoon of wonderful talks here. So we're going to start with Koundinya Vajjha. He works at Intel now. He's a mathematician. He did his, I guess, in the modern world, he has a measure of distinction featured in Quanta magazine. So by that, he's a distinguished mathematician. But now works for Intel on hardware verification, I guess. So he'll be talking about formal verification for mathematics, software, and hardware.
All right. Thank you for inviting me. Thanks everyone for coming. As Siddhartha just mentioned, my talk will be on formal verification for mathematics, software, and hardware. That's quite a broad title. I don't profess to be an expert on everything. So today, I'll try my best to give you an overview of formal verification as I see it. That said, I'll try to also include some of bits of my own work. But if you have any questions, take my answers with a pinch of salt. So, as is traditional, we have to start with the Kepler conjecture. In 1998, Tom Hales and Sam Ferguson provided a 300-page proof of the Kepler conjecture that states, it was proposed by Kepler in 1611, and it states that there's no arrangement of congruent balls in three-dimensional space, no packing, which is denser than the packing that you see there. I think this also works. The cannonball packing, which is a face-centered cubic packing. The proof was submitted, well, it was a proof by exhaustion. They reduced the general case to checking about several hundred thousands of nonlinear inequalities. And there was the traditional mathematics, and there was also the computer code, which verified using interval arithmetic each of those nonlinear inequalities. And they submitted the entire thing to the Annals of Mathematics, and that was published in 2006, but with a disclaimer that the referees had run out of steam and they could not certify the correctness of the computer calculations. Okay, that is story number one. Story number two is the Ariane 5 disaster. On June 4th, 1996, the maiden flight of the Ariane 5 rocket ended in a catastrophic failure 37 seconds after launch. What happened was there was a software bug which caused an overflow exception, and this overflow exception arises from conversion of a 64-bit floating point number into a 16-bit integer. And instead of the software failing gracefully, that caused the inertial reference system to veer off target and the rocket self-destructed. Okay, so that is story number two. Story number three is closer to home. In 1994, a mathematician, Thomas Nicely of Lynchburg College in Virginia, was trying to estimate the numerical value of Brunn's constant, which is the sum of the reciprocals of the twin primes. It was proven to exist, but they didn't have a handle on what the value was, and he was trying to estimate that value. In the process, he started discovering some errors in the computation that he was trying to run. And then he realized that the errors were due to a hardware bug inside this CPU, the Pentium CPU. And the errors were quite noticeable. And then he made that public, and eventually that year, that led Intel to set aside $475 million, and they recalled all of the defective chips, and this was the first recall of a computer chip. So that's story number three. So from all these stories, these are the lessons that we learn. We learned that mathematical proofs are now approaching a level of complexity that trumps traditional referees. If we have unchecked software bugs in safety critical systems, then they can spell disaster. And in order Well, hardware implementations need to ensure that the data paths which compute the actual arithmetic and so on need to ensure that the data paths are correct. Otherwise, if you have a silicon bug, the cost of the escapees is really high. So what can we do? This is where I introduced formal verification. Although I set it up as such, I want to end this talk by saying that it's not a panacea, but for now, since we're at the beginning, formal verification refers to a set of methods which rely on mathematical proof, which, as we all know, is the highest form of assurance, to use mathematical proof to ensure correctness and quality of a design. So in these three fields, mathematics, software, and hardware, we can have formal verification to rigorously verify the proofs of theorems all the way down to the fundamental axioms. In software, it can help us detect bugs that traditional testing misses. And in hardware, it can help us ensure correctness of the circuits before the chips are fabricated. I chose those three stories because they have something or the other to do with formal verification. And let's see what the responses were for each of those stories. So in story number 1, for the Kepler conjecture, Hales launched the FlySpec project in the early 2000s. And this project was funded, and it aimed to formally verify the entire proof. I was fortunate enough to have Hales as my advisor, and I heard lots of stories from him about this. And one of the stories was during the early days of FlySpec, he wondered if he had taken up too much. But 10 years later, remarkably, they, along with a huge international collaboration in three countries, Vietnam, Munich, and the USA, they finally completed that project in 2017. So it used a combination of two proof assistants, Hall, Light, and Isabelle. We'll talk about what those are in a second. But essentially, for now, we can think of them as alternate foundations of mathematics, which help us to deduce or express these mathematical statements in them and prove them. And this is what the statement of the Kepler conjecture looks like in the proof assistant Hall light. This is the statement that they proved. They proved that the Kepler conjecture is equivalent to the statement that for all packings V, there is a constant C and a real number R greater than or equal to 1, such that the cardinality of the packing when intersected with a ball of radius R and centered at 0, the number of balls in that intersection is less than or equal to this quantity. So essentially, they transformed the statement of the Kepler conjecture, which was a statement about density of packings, into the number of spheres that there are in this intersection. So, okay, so story number 2. Now, I admit that I took some liberties here, but I did read this interview which I cite here as I was preparing this lecture. The Ariane 5 disaster was fresh in the mind of Xavier Leroy, a computer scientist, as he worked on what would eventually become the COMCERT project. So the COMCERT project was a similar project. It was a massive undertaking where they proved the correctness of an optimizing C compiler. This is the compiler that when you write down C code, transforms the C code into something into assembly language which the computer can understand. It used the Coq proof assistant. It took 6 person-years of effort. And this is the kind of statement that they proved. They say that for all source programs S and compiler-generated code C, if the compiler applied to the source S produces code C without reporting a compile time error, then the observable behavior of C is one of the possible observable behaviors of S. Now, S you can think of as the source code that you write. C is the assembly language code that is produced by the compiler. And if it does so without a compile time error, then the observable behaviors match. So this is a semantic preservation theorem. Essentially, this says that the compiler does not do something which you don't intend. The key thing here is to write down or specify the observable behaviors, and this you can only do by reading the C language manual and the assembly language and write a formal specification and prove things against that. I'll also touch upon this in a second. I believe they also account for that. Don't quote me on that though. But yeah, you should check out these references. So I made sure I sort of like if you want to read more, you could check out the references. Okay. Okay, so the third response was Intel after the FDiv scenario, the design defect, they invested in formal verification. And in the 30 years since this has happened, formal verification is now part of our day-to-day lives at Intel. And it has got many corner case issues that otherwise would have reached silicon. And for our proofs, we use several in-house and industry standard tools. And the correctness statements that we prove are essentially statements like there is this implementation of the hardware that is supposed to follow a particular specification, and that those two match. Or that a given property, as soon as you have the hardware, for example, satisfies a property like safety and liveness properties that hold of the model. I'll touch upon more of those at the end. Okay, so how do these tools operate? All formal verification tools, software, have the same principles. It is that it is possible to give a mathematical representation or model our system of interest, and typically the system that does the modeling is some sort of logic, and the apparatus of the formal logic allows you to construct statements or properties of that mathematical model, and you assign to the formal symbols of that logic a certain semantics, so that it's ground in reality. And when you prove a property of your mathematical model, you can deduce that the correctness proofs permeate into the real world. Of course, this has its own issues. Very importantly, that the map or the model should not be confused for the territory. Like, for example, you cannot model the real world no matter how hard you try. There are always things that that you will slip, and this is expressed in the maxim that all models are wrong, but some are useful. So it only depends on how accurate the model is for that particular domain. Okay. Yeah, so as I said, FE tools implement a base logic that is expressive enough to model the domain to be validated. And there's a trade-off between expressiveness and automation. Interactive theorem provers and proof assistants have highly expressive logics, and within those logics you can formalize arbitrary mathematics. But because of that expressive power, you have there's no, I mean, I don't want to say there's no automation, but there's less automation. So you can reason about more complex structures, but it requires substantial effort to write the proofs. On the other side of the picture, there are model checkers, SAT and SMT solvers, which trade expressiveness. So the things that they express are not as powerful, but they're more automated. They're sort of push button techniques that you just say, this is the formula that I'm interested in, is it SAT or unsat? And you can efficiently verify small finite state systems and propositional constraints about those systems, but you cannot express richer mathematical properties. Okay. So now I want to get to the meat of the talk, where I want to look at FV across mathematics, software, and hardware. FE for mathematics, all right. So it can be argued that the first formalization effort was about more than 100 years ago, when Russell and Whitehead wrote their Principia Mathematica, which was an extension of, or an implementation of their logicist thesis, which says that all of mathematics can be grounded in formal logic, and they very bravely decided to do the entire formalization by hand without any tool support. And as a result, you get things like this, where it took them 379 pages to prove that 1 + 1 = 2. So yeah, it's an example of FE done by hand with no tool support. So here, maybe I want to shoot off in a philosophical tangent, that maybe today formal verification, maybe it's the logicist thesis taken to the extreme, where we think that everything can be expressed in formal logic. But yeah, something to think about. But Russell, okay, I want to go back and talk a bit about this. So this, as you can see, it was quite complicated. Like, they had 380 pages before they could do any arithmetic. And in his autobiography, Russell stated that he was difficult abstractions. He was not able to deal with more difficult abstractions after writing. So it took a toll on his intellectual prowess, as what he said. But his work, or their work rather, laid the foundation of what would become type theory. And type theory is the basis of modern proof assistants such as Lean and Coq. And if we fast forward a century, large portions of mathematics now are such as like results from algebra analysis and topology and category theory. Some of the people in the audience know more about this than I do, have been rigorously formalized in this proof assistance. Yeah, so mathematics now, I don't want to spend too much time on this because I know that there's a few more talks on this, but it's mathematics of the Lean theorem prover is housed in the MATLAB repository, which I don't know if this number is right, maybe it's 2 million now, and more is being added every day. So for our own work, there was a couple of co-authors and we wanted to study this problem of pack learnability, and some of the tools that we needed were not available in Coq, but the GD monad was something that we realized existed in MATLAB, and this is a probabilistic monad that was already in MATLAB thanks to Johannes Holzel, who kindly helped us with it, and we could use that construction readily in our proofs, and then we could prove certain properties about the pack learnability algorithm. So in the formalization that we carried, we took the simplest possible example, statistical learning theory 101, the simplest example that we saw. We tried to formalize that proof, and then we realized that there are subtle conditions about measurabilities that the authors of those textbooks overlooked, and the results were right, but the proofs as stated were wrong. And this is the sort of thing that you encounter as you do more and more formal verification. You start discovering these subtle bugs, some of them which are quite serious. Okay, so this is my own contribution to MATLAB. I just, as a weekend challenge, I thought maybe I'll just formalize this one cute result that I saw, which is trying to prove that the nth harmonic number was not an integer for n greater than 1. And I saw a proof which used two-adic valuations, and the theory of p-adic valuations was already in MathLib at the time, so I thought I could just use that. And I think one thing is that it's fun. Like, if you're anything like me, where you enjoy really difficult video games, this is quite the challenge, right? So you should definitely try. So FreakVDike has compiled a list of provers, and this is quite dated. This was in 2006, but he compiled a list of 17 provers, in which the irrationality of the square root of 2 has been formalized. We just saw lean. Lean is not part of this list because it didn't exist at the time, but there are a lot of other proof assistants which are capable of expressing mathematics, and the irrationality of the square root of 2 was the benchmark that he had. Some of these I really don't know anything about. Some of these I don't know if they're even used anymore, but I just wanted to show this because there's a lot of them, perhaps too many of them. So Freak was interested in this proposal called the QED manifesto, which was in the early 90s. I think it was Bob Boyer who put out this proposal that we should have a computer-based formal mathematics library, and all of mathematics should be formalized essentially. The project never took off, and Freak has, in that article that I quote there, a couple of interesting reasons why it did not take off. Partly because there were not that many people who were working on that area, formalization of mathematics. But the future is bright. I think the future is now, perhaps, because we've just seen Lean, and in the Lean Zulip chat, if you log on there, you will see fields medalists together with undergraduates. It's really quite remarkable, all working, computer scientists, mathematicians, all working together, formalizing mathematics. And I'm sure you'll hear more about these two things today. Okay, so that was FE for mathematics. Do you have any questions? I'll take a sip of water. Okay, so formal verification for software. So speaking in very general terms, if we want to trust an implementation of, say, your favorite algorithm that you come up with and you implement on a computer, here are the following things that you need to trust. First, you need to check the mathematics behind the algorithm, whether that's sound or not. Or that is, you check a mathematical proof that the algorithm does what it's supposed to do. And then you check that the implementation of the algorithm in your programming language of choice is faithful to the semantics, that you don't miss, or essentially that you implement the algorithm correctly. That's what you need to check. Okay? And then this is what we saw in CompCert. Check that the compiler, or whatever it is that eventually translates your program down to the machine code, preserves the semantics, does not include any extraneous behavior. And you need to check that the silicon which runs the machine code is free of any hardware bugs. All right, so this is the thing that I could come up with. Perhaps there's more. You should also trust that there's no cosmic rays which come in and flip random bits, but you have to stop somewhere. You have to be reasonable, right? Okay, end-to-end proofs like this are really very rare. I know of only one. This is a remarkable paper where they prove that this theorem prover is sound all the way down to the machine code that runs it. And they only do 1, 2, and 3. Of course, we don't expect them to do 4, right? That's the job of someone else. But in most cases, we just content ourselves with 1 and 2. That is, we check that the mathematics behind the algorithms that we implement is true, and that the implementation is correct. Okay, so software verification helps us with 1 and 2, and that's what we need to. That's what we'll look at in just a second. So how is it that our job is easier? Well, in certain proof assistants or theorem provers, you have what is called computational semantics. So essentially, they are alternate foundations of mathematics which come equipped with the notion of what it means to run. So you can run 1 + 1 = 2, and eventually that will get normalized into 2, assuming you've defined your natural numbers correctly. So this means that the implementations of these proof assistants double up as programming languages. So in our case, we can do 1 and 2 in the same environment. So we can reason about and implement programs in the same environment, which is kind of cool. So Lean is its own programming language, but Coq has an extract feature which allows you to express your properties in the environment and then extract that into OCaml that actually runs. You can also extract that to Haskell in Scheme if you want. ACL2 is another example which I wanted to talk about just a second. So ACL2 has this thing it has a model of the x86 instruction set architecture, which is described in about 5,000 pages of Intel in their software development manual. And they have essentially things like which instruction can do what, to what register, and all of that. So it's a specification written for human beings. What they did was this is a period of many years. They formalized the specification of the x86 ISA inside ACL2. And because ACL2 can actually run, they got it to a point where this formal proof artifact can actually boot Linux. And this is like insane if you think about it. Because now you can actually reason about userland processes which actually run on this model. So it's amazing. Probably the only even more amazing fact is that this work was done by an undergraduate. So kids these days. So you should check out the thesis if you're interested. Yeah, Sohail. Okay, so obligatory AI reference here. Say we want to formally verify a piece of software that implements an AI algorithm. Okay, so let's be simple. Let's do reinforcement learning. And let's do the simplest possible reinforcement learning algorithm. It's called value iteration. It doesn't matter if you don't know what that is. Essentially, value iteration is the most basic, and its correctness is usually taken for granted in implementations. And we want to say prove that it actually is correct. How would we do that? So first you write down the pseudocode. This is what it is. I don't want to spend too much time here, but essentially there's a bit of data that you have. You have a Markov decision process. You have an initial value function, and you have a threshold, and you have a discount factor. And you can see that there's a loop here which computes these VNs starting from, it computes VN plus 1 from VN. And you stop when this VNs and VN plus 1s differ uniformly in theta. And you return VN plus 1 as an approximation to your V star, which is the optimal value function. So once you have the optimal value function, you can recover what is called a policy, which will tell you what action you should perform given the state that you're in this reinforcement learning framework. Okay, the details don't matter, but the thing that I want you to pay attention to is that if you just look at this, the correctness of this has an implicit assumption that the VNs approximate V star, right, as n grows larger and larger. So this is implicit in this algorithms, and that's what they do in all implementations as well. So if you want to prove that correct, this is the property that we could prove, and that's what we did in a paper a couple of years ago. We proved in Coq that Vn converges to V star uniformly as n goes to infinity. And we did that using the Banach fixed point theorem. Essentially, this operation, this complicated operation, is actually a contraction mapping on a complete metric space. And so the Vn's here are simply fixed point iterates which eventually converge to the fixed point. And that gives us a machine check proof of correctness of the value iteration algorithm. Okay, so that's what we mean by correctness proof. Of course, you can also do more, right? Once you implement this pseudocode inside KOC, you can also reason about, say, the runtime behavior. In this case, or like how many iterates does it take to get within a certain boundary, and so on and so forth. I mean, those are trivial questions to answer here, but you understand how that would play out for other algorithms as well. Although we didn't do this, you could also use the program extraction to get a piece of OCaml code which implements this algorithm and for which you prove the correctness of. We didn't do this because we used the real numbers, and the real numbers use non-constructive axioms in KOC, so extraction breaks. But if you're really serious, you could find ways around that. I just want to talk a bit about the proof. Formal proofs force you to think in general abstract terms, and frequently doing that helps you figure out the general structure of the argument. And in our case, for value iteration, we realized that we could rephrase the Banach fixed point theorem as a proof rule called metric co-induction, which essentially says that if V is a set which is closed and non-empty, and if the contraction mapping preserves it, then the fixed point is also in that set. This is called co-induction for technical reasons. If you thread through the categorical semantics, you will see that this says that particular coalgebra is final in a category of coalgebras. Yeah, you should look at the details in the reference there. But the reason this is nice is because you do the hard work of the epsilon deltas in one step, and then you can reuse this proof rule in other situations as well. And this is the sort of thing that doing formal verification helps you with. Okay, now to the third part of the talk, which is formal verification for hardware. So there are certain differences when you go to hardware, and we'll talk about them in a second, but there are two basic paradigms. The one that we saw before was equivalence checking. Essentially that, say you have an instruction which computes the absolute value of a 64-bit floating point number. There is a specification for that. Well, absolute value is too simple. Let's do, say, addition. Okay, you can add two floating point numbers in a CPU. There's a specification which is given in the software development manual, and you need to make sure that the specification in that manual agrees with what the RTL implements. Of course, when you write that spec yourself, there's a risk of misspecification, that what if the spec that you write is not accurate. Okay, so the other paradigm is called property verification. Essentially that you have that a design satisfies a set of properties. Say if, like, this particular design has no deadlocks or has mutual exclusion or things like that. And here you have under specification risks, that how many properties are enough, right? You can keep tacking on properties, but you never know if you're there. So in hardware, we usually, as a best practice, use both. We have a team which does FPV, formal property verification, and then we have a theorem which does the actual arithmetic, which is equivalence checking, that kind of thing. So the difference between software and hardware is that it's extremely expensive to do full end-to-end proofs, because the designers, when they write the actual code that makes it to the silicon, there's a lot of churn that happens. Say they speak to the architects and requirements suddenly change, or someone who on the validation side who says that there's a bug in the thing. So they keep changing the spec, or they keep changing the RTL. And so the churn is so much that making sure that you have an end-to-end full proof is really difficult. Okay, it's really expensive. So any FV that we actually do has to be semi-automated. Also, counterexamples are more valuable than proofs, although maybe that's too harsh a statement to make, but in general, the designers, at least the ones that I speak to, they're really appreciative of FE because we can find the corner case bugs that they miss. So I want to talk about the two basic hardware verification workhorse that we have at Intel. Say we want to prove this AND gate correct, okay? And this is just a black box. You can also replace it with say a piece of hardware which does something else. And just for an example, consider this 7 input AND gate which computes the logical AND of all of these 7 inputs. To test it exhaustively, you need 2 to the 7 inputs, and this is called simulation. But if you don't want to have 2 to the 7 cases, you can get away with 1. You model this AND gate in a logic which allows you to tack on symbols to each of these inputs and check if the output is a formula which computes the logical AND of these 7 inputs. The way you do that is through binary decision diagrams, typically. So now one single test case will suffice. You tack on these individual symbolic variables, you let them run, and then you see what formula is computed at the very end, and then you check. However, there you have the overhead of dealing with symbolic variables, which may cause blow-ups in memory. So what you usually do is, you don't need all 7 test cases, right? If any one of these is 0, the other ones you don't really care about, right? So they can be anything. So you can reduce the number of cases by tacking on this X or a don't care value. And this is called abstraction, where you don't care about certain parts of your circuit because the action which happens is only in another part of the hardware. Okay, so now binary logic, Boolean logic, is now extended to ternary logic, and you have all the truth tables of and, or, implies, and equivalence are now extended to this ternary logic. And then now you can use ternary logic to simulate a fewer number of test cases. So to summarize, we need 128 test cases to conventionally simulate an AND gate. In symbolic simulation, you need 1, but you have symbols. In ternary simulation, you need 8 test cases because as soon as one input is 0, the other ones don't matter. And yeah, okay, so now the insight was that you can combine symbolic and ternary to get something which is much better. So both these, if you combine, you get something which is better. And the way you do that is through symbolic indexing. You have symbolic variables PQR to encode each of these 8 test cases. So the idea is that if you have 0, 0, 0 for PQR, that stands for this test case. If you have 1, 1, 1, it stands for this one, and so on, right? So you have 8 of them, 3 symbolic variables, so you have logarithmic number of test cases. Okay. So in other words, you reparameterize your inputs in terms of these PQs and Rs, and then you can check all test cases in one single symbolic simulation run. So, and that's just in 3 variables. So, and This is what the correctness statement of the AND gate looks like when you reparameterize it in terms of the symbolic index variables. Okay, so this leads us to STE, which is called symbolic trajectory evaluation, which is the main verification workhorse and use at Intel. Instead of just the AND gate, you can extend the pieces of hardware that you can simulate by adding temporal logic that you can add, say, this particular bit in 2 cycles satisfies this property. And you can write that as a symbol, and then you simulate using the symbols that you have, and then you check at the very end whether the specification matches the implementation. Essentially, that's how it works. For technical reasons, you don't use 3-valued logic, but you use 4-valued logic. If you want to read the details, you can read this paper, but good luck because it's really hard to read. And this is probably of interest to the folks here. You can use STE to, with theorem proving to patch together several symbolic trajectory evaluation runs in decomposed proof. So, for example, if you have a divider, a hardware divider, you can prove, well, it implements an algorithm, say the SRT algorithm. Usually, the hardware does it in pieces, and so you can have a symbolic trajectory evaluation from, say, the sources to the intermediate stage, and then from the intermediate stage to another stage, and so on. Now, theorem proving can then help you patch together these different STE runs, and then you can get a proof that you start with the inputs, you end up with the output. And Intel uses a in-house tool for this purpose. And this combination has been applied successfully to verify many hardware components the past 30 years at Intel. Okay, so that's simple enough. The other thing is, so this applies to data path verification, the thing I just said, STE. But traditionally, you also have control path, which is the logic in the circuit which directs the flow of the computation. And for control path verification, the main technique used is called model checking. And the way you do that is you have a design, you model that as a finite state machine, and the property to be checked is expressed in this temporal logic again, say as a system Verilog assertion. And example properties that you would want to express are things like, hey, that something should not happen. Say, for example, if you have an operation which takes 3 cycles to run, then 1 cycle before there should not be a dispatch which collides with this one. So things like that, that's safety. Liveness dictates what should eventually happen. So once you express these properties, this engine, the model checking algorithm, traverses the reachable states of the design to verify the property. And if a property fails, it spits out a trace which gives you an exact path in this tree, which tells you that if you do this, if you follow this path, then eventually you'll hit a counterexample which does not satisfy the property. And that is sort of, and then that's reported to the guy who made the design, and then the cycle continues. Okay, so I'm almost near the end, I have plenty of time, but now I just want to say that it's FE, although I have talked about how good it is, it's not a panacea, right? It provides mathematical certainty, catches corner case bugs, but it has its limitations, right? Formal verification is, especially in software and hardware, is only as good as the specification. And there's been many times where the specification has been wrong. And if the spec is wrong, then the proof that you write has no bearing in reality. Formal proofs are hard to write. Their FE engineers are hard to find. And this still makes, and there's a lot of human effort required, right? And also, the thing that we talked about before, model checking, it's very prone to state explosion, right? The finite state machine can only handle so many states. And so there's issues with scale. And the thing that I talked about before, if your model is incomplete, if hardware and software proofs, they take for granted certain things that certain things always happen. So if you have power issues or manufacturing defects, you can't account for that. And it doesn't really catch everything. There are non-functional properties such as performance, side channel attacks, all of that will still need testing. So formal verification is good, but it's good when it's used alongside traditional simulation, and that's what we usually do at Intel. Okay, so I'm at the end of my talk. Happy to take questions.
Yeah, hi.
Hi.
You mentioned, that counterexamples are very valuable to the people who develop these, let's say, chips and stuff. But when you try to do, let's say, formal verification, you would want to prove some correctness property, and if it's not true, you will not be able to prove it.
Yes.
But at what point is there a way to produce a counterexample from your, formal verification process?
The proofs we write usually compare against a specification that we write ourselves. So usually what happens is, if our specification itself is wrong, then, as I said here, there's traditional testing with someone else you have to go talk to someone else that, hey, I'm seeing this, and then you realize, hey, that the spec you wrote was wrong, and so that's how you recover a counterexample. So I guess that's the way you recover a counterexample from a wrong proof, wrong statement, but yeah.
So it would be that specification, and then whether the specification matches the actual thing is testing.
Yes, yeah, pretty much.
Thank you for a wonderful talk. So this is a question about the measurability aspect that you said most statistical learning proofs missed. So I want to understand what is the base or the set on which you're trying to do the learning. Is it a continuum, or is it something that is finite?
Yeah.
And how serious is this gap?
It'll take me a while to remember the details, but it's not serious. The proof was that it had a minor gap. If I remember correctly, it's because it did not, like the proof that we formalized did not account for continuous or like probability measure, which can be like discrete and continuous, like a mixture, a mixed distribution, right? So it did not account for that, things like that. But I don't remember the fix, but yeah, there's a reference that if you want to check out, yeah.
And a follow-up question,
Yes.
because you mentioned the Banach fixed point theorem and its use in the reinforcement learning context of value iterations. The fact that you're using the Banach fixed point theorem suggests that the state space is possibly real, or a Polish space, that general, and then you're, or a Banach space, and you're doing the theorem in that level of generality. But there is the similar issue of measurability that comes to the action space. The value iteration will give you the value and how it evolves.
Yes.
But then there is also the actions that this suggests, and the measurability of that is also something that's under question.
Absolutely, yeah.
Is that something that's addressed?
In this case, the sets S and A are all finite, so we don't really care about measurability.
In that case, do you need the Banach fixed point theorem and its formalization, or is there a simpler approach, because we are looking at finite action spaces, state spaces here? I
think you do need the Banach fixed point theorem, because value iteration proceeds with this iteration, right? And I think, I don't know if there's another approach for value iteration which avoids Banach, but this operation is a contraction on a complete metric space. So, yeah. I mean, that was the approach that we saw and then we formalized.
Yeah, are there any other questions? Okay, maybe we'll thank the speaker again. And the Kotak Center has this little gift for this. Okay, thank you. I should have done the other way.